Okay, hi. So thanks everyone for coming. I realize this is early in the week, and many of you may be jet lagged or tired from travel. Certainly, I am. So my my goal was to talk about the general subject in which I work, communication complexity. Much of the rest of these 2 weeks will be looking at various applications of communication complexity or things that connect to this from the electrical engineering side. And really what I'm about to say, most of what I'm about to say will be old hat to people who in computer science work in communication complexity. So let's get started. I'll actually be covering a lot of results that are really basic things, but I want to make a point here that there is a sense in which studying the upper bounds carefully is useful for proving lower bounds. Okay. So I'm not claiming that every lower bound is proven by some kind of upper bound, but many of them are, including some very important ones, which I will mention right at the end. Okay, so in part 1, my goal will be to just cover some textbook results, okay, and really cover them, like explain in detail what's happening. You may already know this, but perhaps you've forgotten a detail or two, and it will be useful to pick them up. And we're going to focus entirely on one communication problem, and a very simple one called equality. But just by focusing on this, we see a few different ideas, okay, that then come into play in more advanced results, which we will talk about in part 2. And so in part 2, I'll be spending most of my time talking about this paradigm for proving lower bounds called information complexity. This may have got covered in a lot of detail at the very first workshop in the beginning of this semester, so I don't know how many of you were here for it, but here's my take on it. Okay, so let's do part 1. That's the basic setup of communication complexity. You have 2 players. Sometimes you have more than 2 players, but almost throughout the talk we'll have 2 players. Right at the very end we'll look at more. So these 2 players are traditionally called Alice and Bob, and they have inputs X and Y, and they talk to each other to do some computation, and there's a protocol pi which specifies exactly what their interaction is. At the end of the execution of this protocol, one of the players, let's say Bob in this case, comes up with some kind of output, and this output is supposed to be the function value f of x, y, right? So again, this is mostly for people who are not CS, but there are 2 standard terms which we'll use in many, which are sort of polymorphic terms. So cost and complexity. So cost says how much does it cost to run this protocol for some reasonable measure, and in the case of communication complexity, the most reasonable measure is the number of bits exchanged. And we'll also say it's the number of bits exchanged in the worst case run of pi. Okay, so there's nothing random about the input in this case. Yeah. And whenever we have a cost measure, we have a complexity measure for functions. So the complexity of a function is the minimum cost of a protocol that computes this function, right? And I've also said that this protocol pi needs to follow certain rules. So the rules may specify that everything is deterministic, or that the players can use randomness, or that the players can use some kind of shared randomness. So these are different rules for how the protocol is allowed to operate. And depending on which rules are being followed, you have different notions of complexity of the function, right? I'll throw a lot of notation at you in a moment, but this is the general setup. Whenever we have a cost measure, we have a corresponding complexity measure that we can define. Okay, so what does it mean for a protocol to compute the function? So in the deterministic case, it simply means that whatever the protocol outputs has to be the actual function value in all cases. In the randomized case, for some reason my my LaTeX got screwed up here. In the randomized case, the protocol's output must differ from the function value. That's an error with very small probability, say epsilon. And in the case of Boolean functions, which is what we'll be looking at for almost the whole talk, we may as well assume that this error epsilon is 1/3. It doesn't matter whether it's 1/3 or 1 in a trillion, it's the same thing by a standard repetition argument, up to constant factors that give you the same complexity. So you may as well assume 1/3. And we'll use notation like R of f to denote the complexity of the function f under this notion of cost. Okay, so randomized communication cost with error epsilon. And when we don't specify epsilon, it's 1/3, as I was saying. Okay, good. So let's look at our first function and consider various notions of protocol for this function. Right. So this function is equality. This is where all of communication complexity starts. So equality function is given by it's 1 if the two inputs are equal and 0 otherwise. Right. Very simple thing. Okay. So there are several models of communication that you could consider, and they're all important for various things. Hopefully later during these 2 weeks we'll see applications that use one or the other of these models. Yeah, I know for a fact that some of the talks will feature each of these. All right, so in the one-way model, so these models are arranged in increasing order of generality in some sense. Okay, so in the one-way model we don't have any interaction. Alice simply sends a message to Bob, and that's it, and then Bob has to compute whatever the function is. So if you want to talk about the one-way complexity, we'll denote it D with an arrow for deterministic complexity, or R with an arrow for randomized complexity with private coins, and with a superscript pub if you're allowing public coins. So public coins is a situation where you have shared randomness, right? Then we can consider k-round complexity, where k is some parameter. K could be fixed, or it could be growing as a function of n, but slowly in some sense. So we think of this and this is different. In the general case, you're allowing full interaction and there's no restriction on how many rounds can be used. So if you have inputs of length n, you could consider using n rounds for the interaction. Okay, and this, when people just say communication complexity without any other qualifiers, this is what they mean. Okay? So this is increasing level of interaction. So there is actually a level of interaction which is even below one way, which is Alice and Bob don't even talk to each other. Instead, there's a third party which you can call Charlie, or which you can call a referee. That's the traditional name. And what Alice and Bob do is they sketch their respective inputs and send them to a referee, and the referee has to produce the output. Okay. So this is sometimes called simultaneous message complexity, simultaneous complexity, and we'll denote these complexities by using this parallel sign. Okay. Okay, so we are going to take that equality problem and understand what its complexity is in each of these situations, right? Okay. So once again, the results that I'm presenting here are textbook results, but I want to present them in full detail because these ideas come up in other things, right? Okay, so Alice has an n-bit string x, Bob has an n-bit string y. Here's a protocol for the equality problem. It's going to be a randomized protocol, right? So first, before anything begins, we pick a prime between n squared and 2n squared. This is input independent, so Alice and Bob can agree on whatever prime they want to use before anything happens. Okay, so this prime p is known to both parties. Now in the protocol, Alice is going to work, well, Alice and Bob are both going to work over the finite field of order p, fp. So this notation denotes finite field of order p. So Alice is going to pick a random element in this finite field, and she's going to compute a fingerprint. So fingerprint of x using this random element r, and this is defined this way. So we just sum the bit xj, which is either 0 or 1, times r to the j. Okay, so it's some computation in the finite field. She then sends this fingerprint over to Bob. If you look at how much communication that involves, it is you're sending two elements in the finite field, right? R and this other element. Each requires log of p bits, and that's therefore log of n, order log n. Now once Bob receives r, then he at his end can compute the fingerprint of y with respect to r, right? And now he just outputs 1 if both fingerprints are the same. Okay. So simple and basic protocol, you probably all know it, but it's good to have this reminder and to understand some structure in this protocol, which we'll see later. Anyway, so why is this correct? So let's quickly go through the argument. So certainly if x and y are the same, then the fingerprints will be the same. So there's no error in that case. So let's just suppose that x and y are not the same. So if the protocol is wrong, then these two fingerprints must match. And now, crucially, we observe that this fingerprint is a linear function of x. Okay? So you can do fingerprint x minus fingerprint y equals fingerprint of x minus y. So that works. So if you now consider this fingerprint of x minus y and look at that expansion, then you'll see that as a function of r, it's a polynomial in r of degree at most n, and it's also non-zero because x and y are not the same by assumption. Okay. So a non-zero polynomial of degree at most n has at most n roots. So this means there's only n values of r, or at most n values of r, that could make this fingerprint equal to 0. Okay? So if you hit one of those bad values of r, then the protocol is wrong. Otherwise, it's not wrong, right? So the probability of an error is simply n divided by the order of the field, which, if you plug things in, gives you 1 over n. All right. So we have a protocol that communicates log n bits and makes error less than 1/3. In fact, it's less than 1 over n, so it's even better than the 1/3 that we would have shot for. Good. So just as a quick check, how many people had seen this before? Pretty much everybody, I'm guessing, but maybe 1 or 2, fine, sure. Okay, let's look at a different protocol for equality, right? This is very similar to this previous protocol. It also involves fingerprints, but it's a different kind of fingerprint, right? Just putting this out there to show you that there's at least one other kind of fingerprinting, right? And maybe you'll see a use of this fingerprint in one of the talks in the rest of this theme. Okay, so in this case, we consider first the set of all primes up to n squared, right? So this set capital P. This is, of course, common knowledge. It's just set of primes up to n squared. Now in the protocol, Alice is going to pick a random number in this set P. Okay, so basically, she's picked a random prime of size up to n squared, and she's going to compute the following fingerprint. Now in this case, notice that instead of treating x and y as n-bit strings, I'm treating them as integers between 0 and 2 to the n minus 1. I can always do that, right? Just binary representation. So if you treat x as a number and r is another number, you can just do x mod r, right? That's a calculation, fine. So that's the fingerprint. As before, the structure of the rest of the protocol is the same. Alice sends the fingerprint as well as the random value she used to compute the fingerprint. Therefore, Bob can compute the corresponding fingerprint for y, and then they compare fingerprints, and they output 1 if the fingerprints match. So why is this correct? So once again, of course, if x equals y, this is going to be correct. So when does this protocol err? When x is not equal to y. So once again, you have this linearity property. See, x mod r minus y mod r is the same as x minus y mod r. All right. So this protocol is wrong if, well, only if r actually divides x minus y. Okay. Now, how often can that happen? So we picked r at random. What is the probability that it actually divides this number, fixed number x minus y? So to do this, we have to appeal to, well, I guess we are in Paris. It's a great theorem of French mathematics of the 19th century, the prime number theorem. Okay, so the prime number theorem tells us, this line actually, tells us that the size of P, the number of primes up to n squared, is asymptotically n squared divided by natural log of n squared, right? Meanwhile, the number of primes that do divide x minus y by just fairly easy estimation is at most log base 2 of x minus y. Okay, and log base 2 of x minus y is, of course, at most log of n squared. Sorry, what? I have something wrong here. Yeah, pardon me. The first one should be order n here, not order log n. Okay. Sorry. Okay. So my calculation at the bottom is off. Let me do the right one. Okay. So number of primes dividing x minus y is well, log of 2 to the n. Say at most is at most n, and this one is definitely correct. This is n squared over ln n squared. So the probability of an error is at most that number by that number. So we get n divided by n squared over ln n squared, which is at most order log n over n. Okay, all right, sorry. So if these slides are being uploaded somewhere, I will correct them so that the last 3 lines are correct. But anyway, that's the calculation. At any rate, the error is less than 1/3, right? That was the goal. So this is still decreasing in n. All right. So that's 2 different protocols for equality based on the same basic idea of computing a fingerprint and comparing fingerprints. We just have 2 different notions of fingerprint here, right? All right. Okay. So let's go back and look at that first protocol again and abstract something out of it, and then that will give us a new result for equality. Not new in the sense of new, but it's a textbook result, different result. So, so this is what we did for a fingerprint the first time around with this polynomial. And one way to think about that fingerprint is it takes this x1 through xn, consider this as a vector, and it takes the inner product of that with this other vector, which is r squared, r to the n. So it's taking the inner product of our data vector x with some random vector which has a special format, right? So it's powers of r. Now you can write this as multiplying x by some matrix. In this case, the matrix is 1 by n. Okay. All right, but when you take that view, you realize that one can do things a little differently. These computations were all over finite field fp, but you can also do the computations over just plain old f2, so finite field with just 2 elements, right? So this gives us a different protocol for equality. This time it's going to use public randomness. The protocol so far didn't require any shared randomness, but this one will use shared randomness. All right, so using shared randomness, let's do the following. So first of all, we think of Alice and Bob's inputs as being n bit vectors, but instead of bits, you think of them as n elements of f2, right? Because we're going to do arithmetic in f2. Now, using public randomness, Alice and Bob will jointly sample a random matrix of dimensions 2 by n. Okay. Okay. So, so the fingerprint is then r times x as before. So this is a 2-bit thing, right? So r is 2 by n, x is an n vector. Therefore, the result of rx is just a length 2 vector, right? So it's going to have 2 bits. Right. So Alice computes that fingerprint, and then the same old story. Bob computes the same fingerprint. Okay, this part is not quite the same old story. The reason Bob was able to compute the same fingerprint is because r was actually public randomness, right? In this case, Alice could not have sampled r herself and sent it to Bob because the size of r is rather large. It's 2n bits, okay, and we want to avoid having to send 2n bits. Okay. Okay, good. So compare fingerprints, etc. You can check. Again, if x equals y, the protocol is correct. If the protocol is wrong, then what must happen? Again, the linearity thing applies. So it gives us r times x minus y equals 0. So this means if you take the non-zero vector x minus y, there are 2 different inner products with random vectors that both became 0, right? So if you analyze what is the probability that for a fixed non-zero vector, if you take the inner product with a random vector, you get 0, you will find that this probability is exactly 1/2. Okay, that's a nice little puzzle to work out why it's exactly 1/2. But yeah, but it is. So the probability of an error is then just half times half, right? Both things have to go wrong, so it's a quarter, which is less than 1/3. Okay. So that was sort of the reason why I did 2 inner products, so that I want so the error is below my arbitrarily assigned threshold of 1/3. Okay, so. Okay, so let me just mention one thing here. What has this shown? So the complexity of this protocol is what exactly? So the entire thing that Alice sent to the I guess Alice is not sending to Bob here according to my description. We could have done that, but we can do something even better, right? Which is Alice and Bob can both send their fingerprints to the referee, and the referee can do the comparison. Okay, so so that's good because this uses even less interaction than one-way communication. Now, what is being sent to the referee? It's just 2 bits, right? So Rx is just 2 bits. So each party is sending only a constant number of bits to the referee. So this is a constant cost protocol. Okay. Now, the only thing possibly unsatisfying about this is this public randomness. So let's talk about how in general we can convert a protocol that uses public randomness into one that uses private randomness. This is an important idea for people not so familiar with the subject of communication complexity because this idea is often used without mentioning it many times, right? So people will design a protocol with public coins and then say that, okay, we're done, and it's good to know why, because you don't really need public coins in some sense. All right, so so let's say we have some generic protocol pi computing some generic function f, but pi uses a public random string. Okay. So now we're trying to design a new protocol, okay, using pi. We'll change it in some way. So now let the script r denote the set from which pi draws its random string. Okay. Now we'll consider subsets of this set script R. So this script R set could be a very large set. For example, in the previous public coin protocol that I showed you, the random string being used was of length 2n. So this would be the set of all strings of length 2n. Now we're going to consider much smaller subsets of R. We'll see how much smaller in a moment. But a subset of R will be called a core set if the following thing happens. So another term for this would be it's a representative sample with respect to what we're using R for. Okay. So what's happening here? So another way of reading this statement is to say, if you ran the protocol with all the possible strings in script R, then 1/3 of them would lead to a wrong answer, right? At most 1/3 of them would lead to a wrong answer. So now my set S is considered good if, let's say, do I have a typo here? Yeah, I'm sorry, that inequality should be the wrong way. That's a really bad typo. Okay. Sorry, this should say less than or equal to. Okay. So anyway, a set is good if the oops. Oh dear. So I'm considering running the protocol with every R in this set S. Okay, and I'm looking at how many of them are wrong. If I did it with the whole set R, then it would be at most 1/3. And so here, if it's at most 2/5, 2/5 is a little bit more than 1/3. I'm going to say this set S is good. Okay, this is less than or equal to. I'm sorry. This is not PowerPoint, so it's not easy to live change this. Okay. Anyhow, so it's called a core set if it's good at all possible inputs x, y. Okay. Okay. So there's an easy argument using say Chernoff bound shows us that there is a core set of size order n. Okay. Okay. So let's see how do we prove this. The proof is simply just pick this set uniformly at random. Okay, of some particular size. Then just look at the probability that S is actually good at some particular input. Okay, so this is a matter of you expect 1/3 errors. What's the probability that you get more than 2/5 errors? Well, that probability is okay. This thing is too typo ridden. I'm sorry. This ought to say S is not good at x, y. Okay, the probability of being not good is probability of exceeding 2/5. Okay, so actually this and this are consistent. I guess I have to change good to bad, and then everything will be fine. So, yeah. My apologies for this. I blame the jet lag. All right. So, okay, so it's at most some exponential in S, right? And by adjusting the constant suitably, we can make sure that by doing a union bound over all x, y, of which there are 2 to the n times 2 to the n, we have a probability of less than 1. Okay, so this means if you pick the set S at random, there is some probability that it's less than 1 probability that it's not a core set. So there exists a core set of that size. Good. Now, once we do have a core set of that size, we can use it in a protocol as follows. So, see, by definition, a core set means that this is a good enough representative sample of the full set R, right? So let's just use this representative sample. So Alice is going to privately pick, now there's no public randomness here, that's the whole goal. Alice is going to privately pick one of the things in this sample, 1 up to S. So she'll just pick a number from 1 up to S, okay? And then she sends this to Bob, so now Bob has it too. So effectively they've agreed on one of the R's in the set S. And now they simulate the original public coin protocol as though the public coin had generated the string R, right? So we can check that the probability of error has gone up from 1/3 to at most 2/5 by definition of what a core set was. By definition of what a core set was. And the communication is just whatever the communication was in the old protocol plus this added log n term to send this number I over. Okay. Okay, so this is the first of the results that I'm talking about, which actually has a definite provenance. It's Newman's theorem. I mean, the results that I showed you before obviously were obtained at some point or the other, but they're seldom referred to with a specific paper. So, unfortunately, I'm not old enough to know their provenance. They aren't in Yao's. They aren't all in Yao's original paper, which defined communication complexity. That I checked. So anyway, okay. So, one important feature of this protocol is it preserves the whole communication structure of the original protocol. It doesn't add any extra rounds of communication either, because Alice was going to send the first message anyway by convention, and she's sending this extra thing in the first message. She can just add it to what would have been her first message. With one exception, if the original protocol was simultaneous, then this is no longer simultaneous because it involves Alice talking to Bob. Okay? So, other than the simultaneous case, this doesn't break the model of communication. Okay. So, let's see how we can do the same kind of idea, but in the simultaneous model. Okay. Check how we're doing. Okay. So, as we have seen, we have, let's say, some protocol pi using public randomness. We find some core set for this protocol, and the core set is of size order n. And let's just assume that this size is a perfect square. We can do that without loss of generality. And let's say the core set is of size m squared, right? Now, previously, the whole challenge was Alice and Bob needed to agree on one random string in this core set, right? And the way to do that was for Alice to pick it and then send it to Bob. But now we can't do that because we're in the simultaneous model. So instead, we are going to assume that all the random strings in our core set are arranged in this nice grid, square grid. And so Alice is going to pick a row of this grid, and Bob is going to pick a column. And the intersection of these two will end up picking one of the elements. Okay. So how is this done? So Alice is just going to, these are just formulas to say choose things from, choose the ith row, jth column element. So Alice will choose the row, and then she will send to the referee the row index and whatever her message would have been in the original protocol for every possible random string in this row. And then Bob does the same thing with his column. Now, of course, the referee has got lots of different candidates for the message from Alice and the message from Bob, but based on these two, the referee knows where the intersection is. So he knows which element is actually common to this set and this set. And so he is just going to simulate the original protocol, assuming that those two messages came from Alice and Bob, right? So message corresponding to Rij. Okay, you can check this obviously works. And the theorem it gives you is that the randomized simultaneous complexity of any function f is at most square root n times its public coin simultaneous complexity. Okay? So in other words, so let's compare the two theorems we have. So if you don't insist on simultaneity, then converting public coin to private coin adds log n to your complexity. But in the simultaneous case, it multiplies your public coin complexity by root n. Okay? Now, all of these behaviors are tight, and our equality example will show everything, right? So let's see. So let's revisit what we have shown for equality, all of these elementary results. So we've shown that public coin simultaneous complexity is constant. One-way complexity randomized is log n. Then the private coin simultaneous complexity is root n by this previous theorem. And finally, the deterministic complexity, well, we haven't shown anything. We haven't given a deterministic protocol, but we have the trivial one where just Alice sends her input to Bob, and that's complexity n. Okay. Now, it turns out that none of these can be improved. So each of these bounds is optimal, and we're going to prove it. And in proving this, I hope to illustrate this principle of proving lower bounds by using upper bounds. Okay. Okay, so there's only one proof is kind of not in this form. It sort of is a standalone combinatorial argument, but very important combinatorial argument. It's behind basically every result in communication complexity. Whether or not you see it explicitly, this is what is behind every result. It's called the rectangle property, and it says something that's pretty intuitive. So let me just try to show you a picture that will also prove in some sense this result. So consider a communication protocol where we've written down all the inputs of Alice as rows and all the inputs of Bob as columns, and then there's this matrix which tells you, let's say the entries in this matrix are the actual conversation that happens between Alice and Bob, okay, or the transcript of that conversation. So let's say Alice sends a bit, let's say Bob sends a bit to begin this protocol. Why not? So that divides his input space into two parts, right? He sends, let's say, 0 on this part and 1 on this part, and Alice replies with a bit which for each part in this partition divides the input space. So for each part in this partition, Alice divides it into several parts, right? So with her message. And then this goes on for a while, and eventually the protocol ends. Okay. So notice what has happened is that Alice and Bob, their joint knowledge at this point is that their input belongs to one of these various rectangles. Okay. So on some of them, maybe they'll output a 0. On some of them, they'll output a 1. Let's say red means 1 in this case. So if we throw out the zeros and look at just the ones, it tells us that f inverse 1, the set of all inputs where f equals 1, that is a union of some number of rectangles. And the number of such rectangles is at most 2 to the c. Okay, because the sending of each bit basically splits the partition into 2 parts. Okay, so low communication means small number of rectangles. So in order to prove a lower bound, it suffices to prove that your function's structure is such that you will need a large number of rectangles. Okay, so this is very easy to do for the equality function. So if you look at the desired output matrix or truth table for the equality function, then it is just an identity matrix, right? It's a 2 to the n by 2 to the n identity matrix. Now, if you had to cover all the ones in this matrix using rectangles, it's probably clear visually that a single rectangle cannot cover more than one, because then it would end up covering some zeros as well. Therefore, you need at least 2 to the n rectangles. Okay, therefore it follows 2 to the c is at least 2 to the n, and therefore c is at least n. Okay. So this shows us that the complexity of equality is omega n. In fact, it shows that it's greater than or equal to n. So we have the constant nailed too. Okay. Fine. Now, so what have we shown? We've shown that deterministically we have the right complexity, but what about those other randomized complexities? So why are all of those tight? So to understand that, we have to understand what the rectangle property means when you have a randomized protocol. Okay, so private randomness. Right? This thing will also come into play in the very last thing I'll say in the talk, right at the end of this, the second part. But anyway, so you might want to keep this in mind because it's an important idea. So you can formalize a protocol as a labeled binary tree. I didn't have enough skills to make a nice binary tree picture, but I'm sure you can all go with this picture. This is easy. So let's say Alice sends the first bit in the protocol, and if she sends a 0, then we descend into this node. If she sends a 1, we descend into this node. Let's say in this case Bob sends a bit, and maybe in this case Alice is going to send another bit. You can have that. If Bob sends a 0, we descend into this node. If he sends a 1, we descend into this node, and so on, right? So the entire execution of the protocol can be specified by writing down such a binary tree, and of course specifying the logic for how each party says whether to go to this node or that node. Okay. So in the deterministic case, for every node that is labeled Alice, there's going to be a function of Alice's input x, which tells us whether to go to the left or the right. And in the randomized case, it's more or less the same thing, except now the function will give us a probability, and the probability is the probability with which you're going to send a 1, i.e. go to the, let's say, right. Okay. Okay. So now, if you think about, so look at a leaf of such a protocol. So a leaf tells us that the protocol is over and it's time to output something. Let's say output 1 over here. Now, if you ask what is the probability of getting to this leaf, you will find that it's the product of probability of getting from here to here, and probability of getting from here to here, probability of getting from here to here. Now, for every one of these probabilities along these edges, either Alice knows it or Bob knows it. Okay. So Alice can multiply all the probabilities that she knows and arrive at some function rho al, and then Bob can multiply all the probabilities that he knows and arrive at a function rho bl. And the product of these two functions will give you the probability of reaching a particular leaf. Okay. So note that this is a fairly non-trivial observation about the structure. I mean, this is what you get because the whole thing, all these probabilities came out of executing a protocol. So these probabilities can be factored. This distribution on leaves can be factored into two functions, one dependent only on Alice's input, one dependent only on Bob's input. Okay. So this is what I'll call the rectangle property for private random protocols. And it gives us the following idea. Okay, so we're going to prove another upper bound which will imply a lower bound. Okay, so what we'll do is we take a protocol that's using private randomness and we're going to make it deterministic. Okay, So how do we do that? So first of all, if you have a private random protocol with cost at most c, so cost is just the height of this tree. So this means there is a binary tree of height c, and then these functions rho al, rho bl, such that probability of reaching leaf is given by this product. So we can do a simultaneous message deterministic protocol as follows, right? So Alice is going to compute rho ax for rho al of x for each leaf, and then Bob is going to do the same with his function. And then once the referee has these two things, then he can actually compute what's the probability of reaching every particular leaf. So he can sum this over all leaves that output 1, and therefore he knows what's the probability that the protocol will output a 1. Okay, so essentially he has got the execution of the randomized protocol. There's one caveat, of course, that these values are real numbers, right? So you can't really send them. You have to send them to a certain precision. So let's say we are going to send them to a precision of 2 to the minus c minus 3, okay, a little bit less than 2 to the minus c. Okay. So why 2 to the minus c? Well, this guarantees that the estimate is off by how much? So there are at most 2 to the c terms in this summation, because that's how many leaves there are with a binary tree of height c. Okay. And if each estimate is off by 1/8 of 2 to the minus c, then the whole estimate is off by at most 1/8. So if the original protocol had error of at most 1/3, then this 1/8 additive error in estimation doesn't really change the game. So the referee can use this information. Okay. So if you stare at this, you'll see that the amount of communication being used guarantees that we've got a deterministic protocol with cost at most that much. So randomized complexity times 2 raised to randomized complexity. So if you turn this around and make it a lower bound, see, you can view this as a lower bound on randomized complexity, right? Although we designed a protocol and therefore got an upper bound on something, we can view it as a lower bound on something else, and that gives us that equality with randomized communication. Private is at least log n. Okay. So with public coins, we knew it's constant. With private coins, we now know that it is at least log n, even if the protocol is allowed to interact. Our original private coin protocol didn't actually interact, right? It was one way. Okay. Now, okay, good. So, I guess I should check, David. What is the suggested stopping time for the first part? Not quite. 5 minutes late, so suggested is 10. Oh, okay. Yeah, that'll be comfortably done by then. Yeah, sure. So, so now, suppose we have a simultaneous protocol with private coins. We're going to try to use similar ideas to turn this into a public coin simultaneous protocol, right? Let's see what happens. Okay, so we use the same kind of core set idea that we used before. Let me check if I have a typo this time in the definition of good. I think this time it's okay. This one's correct. The inequality is in the correct direction. All right. So we have, so simultaneous protocol has 2 message functions, one for Alice, one for Bob. Let's say Alice sends CA bits and Bob sends CB bits, okay? And the referee is going to compute the output by computing some other function G on the 2 messages, right? Okay, so now let's fix an input for Alice, okay? Fix this input. Now with respect to this fixed input, we'll call a set good at a particular message for Bob if the following happens. Now this may look complicated, but really all it's saying is, if you had used, say, all of R to draw random strings, then there would be a certain probability that the protocol would go ahead and output 1. Okay, so this is what it's saying. So the protocol, this G equals 1 says that the protocol outputs 1. So what is the probability that the protocol outputs 1 if Alice just samples a randomness as she would in pi, versus what is the same probability if Alice samples the randomness only from the set S? So if these two differ by at most 1/3, we will call we'll call this thing good. Okay, so the set is good at that particular message for Bob. Okay, now it's a core set if it's good at all messages from Bob. Okay, so no matter what message Bob sends, if Alice changes her behavior this way, then she's off by at most 1/3 from what the original behavior would have been. Okay, so so as before, we can conclude that there exists a core set of size ordered the number of bits that Bob sends. Okay, if you do the same Chernoff argument, that's what it gives you. Okay. Okay, so then here's a simultaneous protocol that is in fact completely deterministic. So not only am I removing the public randomness, I'm going to remove all randomness, right? So Alice will go ahead and send her message for each r in her core set corresponding to x, right? Remember that we first fixed x and then we got a core set. Okay, so the net result is she's going to send k number of messages, where k is the size of this core set, which is order CB. Okay? And then Bob does the symmetric thing on his end. Now note that each of Alice's messages is CA bits long. So the total length of this message is CA times CB. Likewise, this is also CA times CB. Now using these two sets of messages, the referee is going to go ahead and estimate the probability by just looking at the, in this sample, what's the probability of outputting 1. Okay. So by definition of a core set, things will work correctly, and the complexity this gives you is then CA times CB, well, which is at most square of the original randomized complexity. Okay. Now we've proved an upper bound on D, but you can again view this as a lower bound on R. So if you view it that way, then it tells us that for example, for the equality function, the simultaneous message randomized complexity with private coins has to be square root n. Okay, and we showed that square root n upper bound earlier, so this shows its type. Okay, good. So to summarize, we had these upper bounds and we now have the corresponding lower bounds. Okay, so everything is pretty much as tight as it could be. Okay, good. So this was a quick tour through, I guess, the elements of communication complexity really. But hopefully one or two of you have refreshed your memory about something you may have forgotten. Okay, I should point out that the equality, it seems like I'm obsessed with this equality function, but it's for a good reason. It's very important, has a lot of applications, and there's a lot of interesting nuanced results that you can prove, which I haven't had time to talk about. I just put them up on a slide and with the years to indicate that there's actually fairly recent results on the equality function. So there's a lot more here than might meet the eye. It seems like a very simple thing, a simple function, and it should be possible to say everything quickly, but no. Anyway, so I will just mention one application. I don't have time to really go into applications. So here's a typical one which hopefully will come up later because, well, I mean, things like this will come up later because we're going to see some talks on streaming algorithms. So one basic problem in data streaming is to estimate the number of distinct elements in a stream. It's well known how to do this. Actually, there are very good algorithms for this. But all of these algorithms use randomness to make your space usage sublinear in the length of the input stream. Okay. Now we can prove using the equality function that all these algorithms need to use randomness. If they were deterministic, then a good estimate requires a linear amount of space. Okay. So no space savings without randomness. So this is the typical use of the equality lower bounds, okay, to show that randomness is essential for some task.